as I said, is because the liquids are moving or the fluids are moving, the contaminants that are in the fluids will move with them as well. The key point to remember there is that the groundwater velocity is different from Darcy velocity or the specific discharge that we measure using Darcy's law. Diffusion is another phenomenon that happens in all systems, including subsurface systems. But diffusion is not a very big process or not a very big transport process unless you are in clays. Okay? So, if you are in sands or sand and gravel aquifers, that's usually not a big mechanism, or there is not a big transport, but we do use Fick's law. But the dispersion, which is the net effect of diffusion and differential advection, that's however a very important process. So, it can actually change your transport characteristics quite a bit. Like, so one, it causes mixing in directions other than normal to the groundwater flow, and also it causes mixing in the direction of the groundwater flow. The mixing in the direction of the groundwater flow obviously is the most, and then mixing in the transverse and vertical directions are less, usually like about a tenth less or a fifth less than mixing that takes place in the longitudinal axis. I also showed you, I also talked about how to get dispersivity data. So, one was to do tracer tests. We can either do a force gradient tracer test or a natural gradient tracer test. Natural gradients are obviously better than force gradients, but a lot more expensive to do those. Force gradient tracer tests are done primarily because they're easy to do. But there are places where force gradient test is okay. So, if you are putting a well for drinking water supplies, then you are pumping that well, obviously, like you will be pumping that well, obviously, like so force gradient test might be just fine, because you're saying if I pump this well, what type of contaminants am I going to get, like so in that cases it's okay. But if you want to just see what the transport is in under ambient conditions, a natural gradient test is what you need to do. Okay. So, the transport, if we look at the subsurface, that transport happens. So, when we want to model the subsurface environment, we got to have some sort of a control volume, right? And our control volume is made up of solids and water in the aquifers. Okay, if you are looking at groundwater, the pores are all saturated with water. So, the control volume essentially is a section that we take is a section of the aquifer. Okay, how big or how small should this section be? So, this is my control volume, CV. What do you think the size of this should be? Okay. So, we have some solid grains and we have some pore space, right. So, if I plot porosity here, okay, and if I make my control volume way too small, okay, I might either land on a solid grain or I might land in a pore space. Okay. If I land on a solid grain, my porosity is 0. If I land in pore space, my porosity is 1. Okay. Because all I am seeing in that sample is I am not seeing any more solid grains, I am just seeing liquid. So, it is almost like a pipe. If I make this, on the other hand, if I land here, if I'm taking a sample and if I land here, all I'll see is a grain, I don't see any water, so my porosity is obviously 0. Like, so as I increase the size, okay, I'm going to see, okay, a little bit of sand, little bit of, pore space, so on and so forth, like, So, what will happen is if I plot porosity versus distance, okay, it fluctuates quite a bit and then it becomes constant, okay. Then it starts to increase again, okay. So, this is plotting porosity versus some what we call REV or representative elementary volume. Okay. So if I plot this distance or scale or in terms of volume, if I make my volume very small, my porosity is either 0 or 1, okay, along that axis. And as I increase my grain size, as I increase my size, what happens is I might still see some fluctuations depending on where this box is landing. So if I take the same box, put it at different locations, sometimes I'll get more sand grains, a little bit of pores, sometimes I will get more pores and a little bit of sand. So my porosity kind of fluctuates a little bit till I hit some reasonable size or a reasonable volume where it starts to become constant. Okay. If I start making this even bigger, I will start looking at not a single or a relatively homogeneous media, but I'll start looking at relatively heterogeneous media. Okay, I might have sands and clays or very different geologic units. I may start sampling very different geologic units. So my averaging might cause my porosity to start fluctuating again. So if I make my sample too small, if I make that control volume too small, I won't have a representative porosity or like a representative description of that aquifer in terms of how much pore space is there and how much solid grains are there. If I make it too large, I run into the same problem. So there is some sweet spot somewhere in between where my porosity is, the sample's porosity is representative of the aquifer porosity. Okay, so that's where we want to be located. That's how much we want our control volume to be. Now, usually, so Darcy's law is valid at this scale. Okay, because the Darcy's law, as I said, is based on some average properties. Like so the validity of the Darcy's law lies in that REV being relatively constant. In other words, the porosity is roughly constant. So our samples, if you want to collect a sample, an aquifer sample, we need to take a sample equal to that REV. Okay. If you want to do modeling, our control volume of that model should be equal to that REV. Okay. So the only downside is we don't know what that REV is. Like I mean, theoretically we can define REV and conceptually, understand what REV means, but usually we cannot know what that REV is a priori before we go sampling. So we'll have to do samples at many different scales to figure out where is it that we are getting a porosity that we think is a reasonable porosity for us. So, question?
Does it have any significance on the discretization size if you want to?
Correct. So if you are doing numerical models and you want to put discrete values, that size of the cell is a measure of your REV. So the control volume when you discretize is your little control volume over which you're performing your mass balance or energy balance, and that should be the size of REV. So if you discretize your model and say my model is 100 meters by 100 meters, you have basically said that is the representative elementary volume, or that is the volume that represents, if I take a sample that size, the porosity that I measure will be representative of the porosity of the aquifer. If I make that 1 mile by 1 mile, I'm saying like there is a lot more homogeneity to my system, and I can take a 1 mile by 1 mile sample and I'll get a representative porosity of what my porosity or the true porosity is in that system. So the discretization that you do is a measure of REV. So when we discretize models, we go the other way around. What we are saying is ideally it will be best if we know what the REV is and then we discretize the model. But since we don't know, whatever you discretize, that is your REV, or you're saying a sample is averaged over that little volume that we have taken. Okay, and when we average it, we want a reasonably good average. We don't want a bad average. So what it's saying is that average represents conditions in the aquifer. Okay, so the transport phenomenon, advection and dispersion, happen at the boundaries of our control volume. Okay, so you can think of it as a numerical grid cell, or like you can think of it as an area in the aquifer or the volume in that aquifer over which there is flow taking place, there is movement of flow. So right at this interface of that control volume, that is if I just take a section in the aquifer, right at that interface, I'll call this x. This is the x plus delta x, okay. So, but there's also y plus delta y, z plus delta z. So there are, like, it's actually a three-dimensional cube. And what we say is the flux due to advection and dispersion happen at that interface of that control volume. Okay. So how do we write our flux? Vc is my advective flux, and then dispersive flux over del x. Okay. And of course, that derivative is are all measured at that x. So if I want to measure that x, I assume that there is a small variability around it, and then I take the gradient right at that midpoint. So that interface would be my midpoint, and I would take a distance a little bit on this side, a little bit on that side, and see what that gradient is to calculate this gradient. Similarly, on this side, I have J advection Vc now measured at delta x plus x, and then J dispersion, which is equal to minus d del c over del x measured at x plus delta x. Okay. So I'm using partials because there could also be a del c over del y and del c over del z terms in x and y and z axis. You can write the same thing. You can also envision control volumes in cylindrical coordinates, especially if you're looking at pumping in a well. Your coordinate system is cylindrical because there's water flowing in. So you will represent it using a distance and an angle instead of x and y. And you could have z as well, like, so there would be two distances. One is the radial distance, one is the vertical distance, and the other one is the angle associated with it. So you can do it in polar coordinates if you want, which are like two angles. The coordinate system doesn't matter. What it is whatever the volume that you're measuring is representative of the aquifer properties. That's the definition of a control volume. If you arbitrarily define control volume, what you have said is that is my representative area over which I'm averaging my properties. Okay. By saying we're averaging the properties, whatever is happening at a scale smaller than that representative elementary volume is neglected. Okay. We don't explicitly consider that process. Okay. We are only considering the average of that process up on the top. So what about inside the control volume? So the solute got in, it's moving, and it gets out. So I'm able to define what's happening at these two boundaries using the material I learned yesterday. So what about inside that control volume? What could go on inside that control volume? So reactions can go on in that control volume. So reactions happen here. Okay. So there are two types of reactions that can happen: physical reactions and chemical reactions. So we tend to separate out, at least in the groundwater literature, we tend to say when we say reaction, it means that the chemical has undergone some transformation. So we started off with chemical A. When it reacts, it becomes chemical B. Okay. So only then we call that a reaction. There could also be a physical reaction. The reason there is a physical reaction is I have some pores, I have some solid matrix, and I have some water flowing across. A solute can actually get onto the solid matrix, or a solute that's on the solid matrix can go back into that water. Okay. So we call this interface mass transfer, or partitioning is, or soil water partitioning or sediment water partitioning is one other common way to say it. But they both are reactions in some sense. One is a phase change reaction. We are taking a chemical, we are not changing its constituents, or the composition of the chemical, we are just taking it from one phase to another. So, the most common groundwater interface mass transfer is a chemical going from being in liquid phase to a solid phase. As I talked before, right at the water table you are at connection with atmosphere. So, some of the volatiles can actually move from liquid phase into vapor phase. That's possible. That certainly happens in the Vadose zone because there is there is air in that pores. Okay, so transport can happen. So the reactions are what take place inside your reactor or inside that control volume, and then that inflow and outflow happen at the interface of that control volume. Okay. And the other assumption that we make is this control volume is well mixed. Okay. So, because remember we are only taking average properties of what is happening in the control volume. So, what we are saying is our control volume, if I sample anywhere in that control volume, I will see the same concentration in the liquid phase and in the solid phase. That again is not true, that is an assumption, but again what we are measuring is an average concentration, not necessarily the real concentration that is there. Okay. So, given this assumption that our reactor is well mixed, would also indicate that you do not want to make your representative elementary volume very big, because if you make it very big, you are assuming that your entire aquifer, if I only had one control volume over the entire aquifer, I will be assuming that it is a well mixed reactor, which obviously is not what it is. Okay. If I make it too small, then I will have infinite number of control volumes. That simulates, if I have a infinite number of CFSTRs in series, that is the same as a plug flow reactor, because the residence time is virtually 0. There is no time for it to, it will keep on moving. So our aquifer in some ways behaves as something in between a plug flow reactor and a CFSTR, which means there are a finite number of control volumes, each control volume mimicking a CFSTR. And our system has two phases, solid phase and water phase. Okay. Because there is solid phase and water phase, our chemicals can actually partition or go from solid phase to liquid phase to water phase. Reactions are where the chemical gets transformed from A to B. Okay. So just like with transport, these are what are called fate processes, because they are not causing the chemical to move, but they do decide the eventual concentration or the fate of that contaminant. So, when we talk about fate and transport of contaminants, the reactions and mass transfer are your fate processes, and then advection and dispersion are your transport processes. What other processes can happen? Now, what other types of reactions can happen in your aquifer? The solution, that is a liquid-liquid mass transfer. Okay. So, yeah, you could have two fluids in your system, okay, and that are immiscible, and things can actually move from one liquid phase to another liquid phase. So, that is possible. So, we can certainly have some in the Vadose zone. We have air, so there could be volatilization or mass transfer between the vapor phase and the liquid phase. Very rarely do you have a solid phase to vapor phase mass transfer, because there is usually a small coating of water on most grains, sand grains, okay, unless you have a very highly organic or a hydrophobic like peat or histosols, which are organic soils, which are very small, or you'll find them near wetlands, or you'll find them in some places, but on bogs. But generally speaking, there is a monolayer or a very thin layer of water that coats the soil, and it's extremely difficult to pull it out. Even though you evaporate it, you will still not be able to get it out, because that water is held by London van der Waals forces, which is a much stronger force at very small distances than gravity or latent. So, you need to put in a lot of heat. You literally have to boil it, change the water from liquid phase to solid or vapor phase and then get rid of it. So unless you happen to be in some very extreme desert-like conditions, that usually doesn't happen, even in the hottest of our days like today. So we are in typically a water-bearing system. So a direct contact of vapor with soil is very rare. It does happen, and they've been reported to happen in certain places, like in Nevada and other desert-like aquifers. But generally, you don't see that. Like it's more an exception than the norm. So what else can happen? What other types of reactions can happen? Biodegradation. Okay, so degradation is a type of reaction which means the chemical that I'm interested in is going down in concentration, right? So we are saying we're degrading that chemical, or we're removing that chemical. We could also have reactions where the chemical that's of interest to us is actually increasing in concentration. So that would be a production type reaction, like we are producing the chemical as opposed to removing the chemical. Now the degradation or these reactions are typically controlled by two things. One is it's a chemical reaction, a strictly chemical reaction. So we call those abiotic reactions. Of course, the other one is biotic, which is driven by some microbes. Okay? So abiotic reactions, so that's strictly chemical reactions. You have chemical A, and because of the conditions, turn into chemical B. The one that's most present in water is water. Obviously, in the aquifer is water. The most abundant chemical in the aquifer is water. And because it's the most abundant chemical, the reaction that's very common is hydrolysis, which is the chemical reacting with water. Okay? So that's one type of reactions. What other type of abiotic reactions can take place? Elimination. Elimination is another reaction. So what we basically do is remove one type of chemical out. Okay. So I talked about reductive dechlorination, where we are actually trying to remove some things. That's a type of elimination reaction. Like there are many other types of elimination reactions that can happen. They can be, some of these elimination reactions are microbially mediated. Some of them they are mediated by strictly chemical transfers, so there could be an abiotic component and a biotic component associated with it. What else can happen? What do you think is the pH of groundwater? So, how many are going less than 7? Greater than 8.59? So most likely groundwater will be in near neutral pH conditions, like 6.5 to 8.5. There are places like in limestone aquifers where your pH can be very high. It can be in the 9, very rarely in the 10 range. You will never see something more than 10. But if you have a limestone, lot of limestone, you are basically adding a strong base to that water by dissolution. So your pH tends to go up. You could have some acid mine drainage sites where people have actually mined for acid. So they add acid to the soil to mine out metals, and then that acid kind of leaches and gets into groundwater. And of course, you're adding acid to the water, so your pH goes down. So there are sites where pH can be like 3 or 4 that virtually will kill any microbial reactions that take place in that aquifer. Similarly, if you take it to very high pH, that virtually eliminates most of the microbial reactions that can take place. At that very extremes, all you have are like abiotic reactions. You don't have abiotic reactions. You can have acid-base reactions, just like you do in surface water. What's the biggest driver? What would be the big difference between acid-base reactions that are taking place in that, in a surface water system versus a groundwater system? So we all know acid-base chemistry, right? We all know carbon dioxide chemistry. So there is raindrop in the clouds. The pH of that raindrop is what? that is probably the most pristine water on this in this planet, like so that raindrop, because it's gone through a whole bunch of ionization process, because because it's in the atmosphere, it's subject to a lot of ionization, like radiation, so that water is fairly clean, like it's very sterile, like so it's about 7, so that's, you will have pH of 7. Now that raindrop leaves the atmosphere and decides to come down and visit us on Earth. So it's coming down. What happens? It's interacting with the gases, right? So what is the most abundant gas in the atmosphere? CO2 is the most abundant gas. That will be a few centuries from now if the global warming continues. Okay. Nitrogen is the most abundant, like about 75% of your atmosphere is made up of nitrogen. Okay. What percent is CO2? Yeah, like 0.12 or like point, so it's a very small percent, about 10 to 12%. Okay, what percentage is oxygen? About 21%. Like so even though CO2 is very small, luckily for us, CO2 is very small. It's very soluble in water. Okay, people have made billions of dollars putting CO2 in water. Okay, every time you drink a Coke, you are consuming a product that's pH 2. With just carbon dioxide and some sugar in it, like so somebody became a billionaire by assuming, hey, this is soluble, let's just go put it in and then sell it to people, like so so CO2 gets dissolved in water and dissociates to form carbonic acid. First it forms carbonic acid, then it dissociates, forms bicarbonate and carbonate. Depending on the pH, one of these 3 species is going to dominate, right? Under neutral pH conditions, bicarbonate dominates. If you have low pH conditions, carbonic acid, it will be in the carbonic acid form, and if it's in a very high pH, you will have it in the carbonate form, like so in between 4.5 to 10.3, bicarbonate is the dominant. Doesn't mean that the other two chemicals don't exist, other 2 species don't exist, but they exist in much smaller ratios. You're just changing the ratios of these carbon species. Of course, people talked about acid rain back in the day. When I was growing up, there was a lot of talk of acid rain. Calcutta used to be in the news for its acid rain, like but all rain is acidic because it's got carbonic acid in it. Now, if you add sulfuric acid to it, then it becomes, then you have sulfur dioxide, like and you have sulfur chemistry going in there, and that's that further pushes the pH down. Okay, what else can we put in into the water? What other acid can go into that water? What is the most abundant gas? Okay, so you could have nitrous acid or NOx. Okay, so when people talk about air pollution, they talk about NOx, which is basically nitrate and nitrite, and when they dissolve in water, they form nitric acid or nitrous acid, and that can dissociate and further drive the pH down. By the time the water hits the ground, pH is what do you think the pH of water that just fell off from the atmosphere into a pond? Less than 7, greater than 7? Less than 7, obviously you're adding acid, so the pH, you're driving the pH down. Greater than 1? Greater than 2? No? What happens if we drink something that has a pH of 2? Okay, every time you drink Coke, you're drinking something that's pH 2. Okay, so it's supersaturated with carbon dioxide, but the pH is typically around 4.5 to 5, like so it goes down. If it goes further down from there to 3 or 2, then that's when we used to call it acid rain, like so normally the pH would go down because of carbonic acid, but now if you add sulfuric acid and nitrous acid to it, you'll further drive the pH down. So normally lakes and rivers have a pH around like 4.55. Okay, but they react with the sediments and then they add some base, especially if you have limestone and things like that which are more basic, they end up titrating that water, which is acidic water, and the pH starts to go back up again to like 6 or 7. So, if the water was not in contact with any soil or sediments, its pH would be, the rainwater would have a pH of about 4.5 to 5. And then, but it does come into contact with those sediments, which usually has basic, which gives you some base added to that water, and that jumps the pH back up to 57. What we see a lot of species, we do have some carbonate species in aquifers, like especially calcium carbonate. It's a very common, and then aluminum hydroxide, calcium carbonate, are very common, compounds that you will find in soils. Like soils are layered aluminum silicates. Okay, so there is alumina and silica in most clays, and there is siloxane cavities in sands. So there is some type of either calcium or sodium or potassium, some cation that gets added to that water as that water moves through. So just like so your water might have come from the atmosphere, it was acidic, reacted with the surface soils, it drove the pH back up to about like 6.57. Now it's moving through your groundwater or through your soil, and now it's leaching. Now it's meeting carbon dioxide again because you have calcium carbonate or carbonate minerals in your aquifers. So it will drive the pH down again. So not as bad as atmosphere because you have a long path, several kilometers to travel in the atmosphere, and there is a lot more abundance of gas. Here it's a little bit less. So, but you do see your pH changing a little bit, typically in the 6.5 to 8.5 range, depending on what it comes up with. Okay, so the other thing that happens in groundwater systems that makes it very active for reactions are the presence of microbes. Okay, why are microbes there in groundwater? What type of microbes do you think are there in groundwater? You could have some aerobes, but generally they end up consuming all the oxygen. So in the surface portions, you will have aerobes because you're in contact with the atmosphere, and as you go deeper, you will quickly turn anoxic or into anaerobic conditions. So you will have quite a bit of anaerobic materials. Okay, so when we add nitrate through septic tanks, microbes that can respire nitrate to create hydrogen sulfide become important. Those are like nitrate reducers. If you have sulfates, then you have sulfate reducers. If nothing, there's a lot of iron, so there are microbes that change iron, like the iron reducing bacteria. There are some bacteria that actually oxidize iron, like they do the exact opposite. So just like we breathe in oxygen and breathe out carbon dioxide, or so we are told when we are growing up, we breathe in air, we breathe out air, but with relatively different amounts of carbon dioxide and oxygen in, the microbes use different things, right? So what does that do to your pH or to your water? So you have aerobes, they are respiring, right? Simplest case. They take up oxygen, give out carbon dioxide, right? So what happened there? What type of a reaction is that? So you have some chemical from CO2 plus H2O, right? So if this is some organic chemical, what is that? What's that type of reaction called? That's an oxidation reaction. So everything, sometimes something oxidizes, something has to reduce, right? So this is what we call a redox reaction. And oxygen is not the only species that causes removal of electrons is oxidation, addition of electrons is reduction. So same thing, like anytime you can add or remove electrons, you are changing the oxidation potential. Okay. And in terms of reactions, okay, there is usually an activation energy that's needed, or there is a minimum threshold of energy, and you have to overcome that threshold for that reaction to take place. Okay. So if you don't overcome that activation energy, you won't have that reaction. So spontaneous reactions are reactions that have very low activation energy. So the reaction happens instantaneously in that direction. In the opposite direction, the reaction is very slow because the activation energy is very high. You can't overcome that thermodynamic threshold. Okay. So in terms of redox and in terms of electronegative potential, so redox can be measured using the same concepts that we use in a cell, so because you've got a positive charge and a negative charge, these charges have to move. What is the best or the highest or the one that has the most affinity or the biggest reaction, so what type of microbes offer the best opportunity for reactions? Everything is oxidation reduction, but anything that has oxygen in it, so aerobes that actually make use of oxygen to convert to carbon dioxide. So if you have aerobes and anaerobes, aerobes will outcompete anaerobes, because their activation energy is very low, so that reaction goes faster. Okay. Among anaerobes, there is actually a pecking order, so the nitrate reducers do better than sulfate reducers, which do better than ion reducers, and eventually the methanogens, which are basically taking methane, or they're taking CO2 and making methane, so they're reducing CO2 or pulling that oxygen out of that CO2 and forming CH4, which is a reduced form of carbon, so that is the worst. That reaction has a very high activation energy. So reactions generally proceed from aerobic reactions all the way to methanogens. Yes, what about facultative microorganisms? Facultative microorganisms essentially have multiple breathing modes, so what they do is if there is oxygen, they sense oxygen and then they use oxygen, because that is still the easiest one to convert. If they cannot do that, then once the oxygen goes away, they shut that portion of the nose and open another nose and start respiring from another, they use sulfate reducers or nitrate reducers. It depends on where they are in the oxygen chain. A lot of them do well at the nitrate sulfate levels, but if they start going down, you will not see facultative bacteria. You will strictly see anaerobes or anaerobic species once you go past nitrate or go past sulfate, under very harsh conditions, especially if you have a system that goes aerobic and anaerobic, you tend to see a lot more facultative bacteria because they have to adapt to the condition that their oxygen and nitrogen are changing. Okay. There was a point in time in this earth when there was no oxygen, right, and the only microbes we had were all anaerobic. Okay. Then plants evolved and there was photosynthesis, and what does photosynthesis do? It converts carbon dioxide to oxygen, right? So when that happened, oxygen was a pollutant, okay, because it literally killed all the anaerobic microbes. Okay. So luckily for us, that's not a pollutant for us, but the microbes that were living there back before humans were there on this earth all died because of plants, okay, and plants doing respiration and creating oxygen. Okay. So the only type of microbes, very anaerobic microbes that you're going to see are in very deep groundwater environments where it's completely anaerobic, or in sediments, in very highly contaminated sediments, or sediment bogs in the bottom of the lakes, large lakes, where there is not enough oxygen, going to that lake, and then it becomes so. So those types of species that are there are probably the oldest inhabitants of this earth. Okay. So those anaerobes are probably one of the oldest inhabitants of this earth. This earth belongs to them. We are just borrowing it by adding a pollutant. I mean, we just added a pollutant. The plants just added a pollutant. We didn't. Okay. So which paved for humans to come in because there was plenty of oxygen or other higher level mammals or organisms to evolve. So redox reactions happen. Acid base reactions happen. Hydrolysis reaction happens. So there's a variety of reactions that take place in groundwater systems. Okay. We literally cannot study every reaction that's taking place. So what we try to do is say, okay, this reaction is doing this, this reaction is doing this, this reaction is doing this. The net effect of this reaction is what I'm going to model, or like I'm going to model this. Okay. Sometimes we may have an interest in modeling a specific type of reaction, but by and large, when we model reactions, what we assume is that the reactions all have a net effect. Okay. And that net effect is what I want to model. Okay. And when we talk about reactions, what is the most fundamental concept to describe a reaction? Okay. What's that? First, it should be soluble in water. So let's assume a pollutant that is soluble in water. Okay. To keep our discussion simple. Okay. So what is the most fundamental concept that describes reactions? Something you probably first encountered in your 9th grade. Probably saw it several times since. What does law of mass action say? I have then what? So I have a reaction that looks like that. Okay. Or just put, or the way we usually write. Right. So we have A moles of A reacting with B moles of B, and to form C moles of C and D. This double arrow represents that it's a reversible reaction. So the reaction can go in both directions. Okay. And how do we write law of mass action? What does the law of mass action tells us? It tells us that okay. So there is some ratio that holds true, which is proportional to the molar concentrations or the molar, raised to the power of the number of moles required for that reaction to happen, right? So this is what law of mass action says. So when we put this reversible, what does that mean? So when this reaction is happening, so there is some activation energy associated with this reaction, right? So how does this reaction happen at the molecular scale? So you have some molecules of A in that liquid, some molecules of B in that liquid, they collide, and the collision process creates C and D. So like so for the reactions to happen, the molecules have to collide. Okay. If the molecules don't collide with each other, there won't be any reaction. Like so if I put a beaker of sulfuric acid here and a beaker of sodium hydroxide here, there is no way they're reacting. Like only when I mix them and collide them that I'll form, sodium sulfate and water. So so for that to happen, there has to be some collisions or some reactions. Okay. What it also says is that the rate of forward reaction. So this is the rate at which forward reaction is taking place. This is the reverse reaction. What it's saying is that the reaction is fairly fast, that it's going in both directions. So the thermodynamics is such that a chemical reaction, essentially like any other system, tends to go to its minimum energy state. Okay? So, it wants to go from the lowest possible potential energy that can be in that reactor is what it's striving to do. In doing so, it's forming this many moles, and there is some sort of a ratio, or like it's saying if I get to this ratio, I'm going to stop. Like the reaction is not stopping. All it's saying is every time I convert these reactants to these products are also reacting to become reactions. Okay? So what this type of reversible reaction tells us is the thermodynamics is such that the thermodynamic conditions are such that both these reactions can happen under ambient conditions or the conditions in your reactor. Okay? And typically acid-base reactions are very fast. Redox reactions tend to be fairly fast unless you get rid of some. If you deplete oxygen, then you're in, one of the reactant is gone, and then it becomes a completely different story. But generally speaking, if you have enough products and enough reactants, fast reactions tend to hit this, tend to be reversible. Okay. When the reaction goes fast, we model that systems using what? We can define those systems. When the reaction goes fast means that reactions, all those reactants have hit that thermodynamic minimum. Okay. So, when that happens, then the rate at which the reactants are reacting to form products is the same as the rate at which the products are reacting to form reactants, right. So, so when those two rates become equal, then we have equilibrium. So, if one of the rates is much higher than the other, the reaction will proceed in that direction. Okay. In some instances, one of the rates is so much more higher than the other, then we have relatively inert substances. Okay. So, the rate to convert graphite to diamond is ridiculously high. So, which is why diamond is a very expensive piece of stone, right, because that reaction does not take place very easily. You have to go several miles under the earth to get the temperature and pressure you want for that reaction to actually take place. On the other hand, you can burn diamond. Who wouldn't? That sane mind would, but if you do, you will end up forming carbon dioxide or graphite, and that's a relatively easily process. We can do it on the surface of the earth. Like, I wouldn't recommend doing it, but you will be just a few $1,000s shy of, or like, but it's possible. So, what does equilibrium suggest? The equilibrium. So, one way to model is to use what's called as equilibrium. And in the equilibrium, the rate of forward reaction is equal to the rate of reverse reaction, which means we need to know how to write the rate of reverse and forward reaction, right? How do we write these rates? Okay. So, I will write a much simpler reaction. A is going to be, okay. So, how do we write reaction rates? And I will make it reversible. Okay. So, reaction of A going to B equals, we put a minus sign? We'll put a minus sign? Okay, we'll put a minus sign. What else? Okay. Firstly, the rate of this rate means something is changing with time. Okay. So, first thing we are going to write it is, it's the rate at which some product is being consumed, A is being consumed. Okay. It's equal to what? So, equal to some k, little k, right, into, do we want to put this concentration or this concentration? B? A? How many of you want to put A there? A with a minus sign. Okay, now we have a third one. A with a minus sign, and B. Two right answers here, one answer is wrong. Yeah, you need to have a minus sign, and you can put A, or you can put K is also a valid expression. This is just telling you it's proportional to the rate at which B is being generated. This it's saying is a proportional to rate A is being written. Okay. Of course, it's not always that when you said like the molecules have to react means they have to collide with each other. So this could be raised to some power. Okay. So it can be any power. Generally speaking, the power to which this is raised is called correct order of the reaction. Okay. So does it have to be an integer? Okay. Can it be negative? Yes? If it's negative, what does it mean? Okay. Possible? Possible. Okay. Can it be fraction? Can it be 0.25, 0.3? It can be. Okay. What do you think is the upper limit to this number? Can it be infinity? Can it be 100? Can it be 10? What's the biggest number that you've seen? Can it be 0? It can be 0, right? We all know zero order reaction. Okay. Can it be 1? Sure, it can be 1, right? Can it be 2? It's called second order reaction. Can there be 3? Have you seen a third order reaction in your environmental engineering textbooks or chemical kinetics textbooks? Why do you think we stop at 2? Well, that's a different, we'll get to multi-component, but for the reaction to happen, they have to, chemicals have to collide, right? So the chances of 3 molecules colliding at the same time, the probability is very, very small. Okay. The chances of 2 molecules or 2 molecules of the same type colliding or some ratio that comes down to 2 is possible. Okay. So remember, when we write chemical formulas and we say 2 moles of this react to form 3 moles of this or whatnot, that is what chemists call an empirical equation. The 2 and 3 are just relative, like so I can make it 1 and 1.5 if I want, like I can make it 0.5 and approximate factor. Those factors is what's important. Okay. So really third order reaction, if you think about it in a very basic level, would be 3 molecules coming and colliding at the same time to form that reaction. And from statistics, if you are moving randomly, there is a good chance you will collide into somebody, but the fact that you too will collide with some third person is a very, very small probability. Like if I randomly ask you to bump into each other, unless you really, really are non-random and move and actually hit someone randomly, that possibility is very small. So which is why we don't see reactions of third order, like so third order reactions. So upper limit is kind of very close to 3, like so you can see an order 2.5, 2.6 sometimes, but you will never see 3. Sometimes you will see reactions that are called autocatalytic reactions. What are autocatalytic reactions? That's an example of autocatalytic reaction. What's another good example of autocatalytic reaction? So if have we seen this equation? So what is this Monod kinetics? Where do we use it? So a lot of microbial reactions tend to be limited by some compound. Okay. Remember, when the reaction takes place, you need to have, when was the reaction stop? The reaction never stops as long as you have enough products and reactants. The only time the reaction stops is you take away one of them. Okay. So if it's a forward reaction, then you have to take away the reactants. You have to exhaust that reactions. Sometimes the reverse reaction doesn't happen because one of the products is gas and it just escapes. So there's not enough substrate available for the reverse reaction to take place. Like, so we only have reaction in one direction because technically that's not a system where the other reaction, the other reaction has no chance because it doesn't have all the ingredients necessary for the reaction to go, even the thermodynamics may be favorable. What Monod does is it basically, this term here, C, it actually is writing that the rate of change of your substrate is directly proportional to your biomass. Okay. Because the substrate is being consumed to form biomass, right? You're just changing carbon from one form to another form, basically. Like, and what this C does is it basically, this C over C plus C basically tells you that if I had infinite amount of substrate in my system, the reaction would proceed at this rate, or the mu max rate. But I don't have infinite amount of substrate in my system, because at some point the substrate goes away and I end up getting, this limitation is because it's substrate dependent. Okay, so this is form of an autocatalytic reaction because the concentration of the substrate determines the rate at which the reaction is taking place. The more substrate I have, the faster will be the reaction. The less substrate I have, the less will be the reaction. So the reaction is controlled by how much of the product or the reactant that I have. Okay. If it was equilibrium, it doesn't matter, like, because the proportionalities stay the same. Like, this is what the law of mass action tells us. Okay. But now we are only looking at one side. When we look at reactions that predominantly move in one direction over the other, those reactions are called. So if you have a reaction, this is your reaction, right? This implies that this reaction is just as likely as this reaction, thermodynamically. Now if I remove this and were to put this, what does that mean? It's a irreversible reaction. It doesn't mean that the reaction cannot proceed in this direction, it just means that thermodynamically it's not favorable at that point. Okay? And when we have irreversible reactions, that reaction will stop at some point. Why? Because you will run out of your reactants. Okay? And it also means, so then we use kinetic descriptions. Okay? Kinetics basically tells us the rate at which that reaction is proceeding. Okay? And a complex reaction, let's say A, and forms B, okay, very common in biological reactions. Like, we form some intermediate compound because we need some sort of a catalyst for this reaction to take place. So we have some catalyst, and that catalyst reacts, okay, to form some compound, and then eventually it will form that final compound. The catalyst comes out and that reaction is formed. Okay. or we can put something like not a carbon bond, but ABC, and it will dissociate, the catalyst comes back, right. So these types of reactions tend to be controlled by how much catalyst is there. So those types of reactions are all autocatalytic reactions. They are called autocatalytic because the more catalyst I have, the faster will be that reaction. The less catalyst I have, the less faster will be the reaction. So the substrate in Monod kinetics acts like a catalyst, basically, like it's because it's what facilitates that reaction. It's not truly a catalyst because we don't recover it back. It becomes carbon dioxide at some point. So technically, we shouldn't call it a catalyst, but it kind of serves that same purpose. So what type? So this is, so when we write reaction rates, we are giving a kinetic description of that reaction. So we are saying that that reaction proceeds at different times at, and the concentration changes over time. The rate at which the reaction takes place sometimes stays constant, sometimes it doesn't stay constant. It depends on the concentration. Okay? So what are the most basic forms of reactions? So how do we get reaction data? So I want to put reaction. Okay, I have a chemical that I'm tracking in my groundwater, and that chemical will undergo reactions. Okay, so now it's your job, and I want to model this, which means I want to write a flux and I want to write a loading term, because if I have loading terms, I can just plug them all together. Right. So how do I write loading and flux terms for reactions? So we know there is something called a reaction rate, right, dCdt. Okay. This is, right. So this is milligrams per liter. This is time. Okay. If I want to get a loading term, I'll get milligrams per time or mass per time. Okay. So what I have is this from my rate term, and if I multiply it times the volume, which will be my control volume, I will get my reactor rate. Okay. Right. So is my loading due to reaction. Okay. So we use Darcy's law to get our advective loading, multiply times concentration. We multiply, like, average linear velocity with the concentration, or the flow rate with the concentration. We get that. Then we get diffusive fluxes coming into our system using Fick's law, right, or dispersive fluxes using Fick's law. Now we have a loading term of what's happening in the reactor. Flux, you just divide that by the area over which that reaction is taking place, which is very hard to determine in a reactor, like, because the reaction is taking place everywhere. So we generally write a loading term, and that loading term basically is that rate of that reaction. So if you have a kinetic description, it is the rate of that reaction times the volume. Now what is that volume that we are interested in porous medium? If you have a batch reactor set up in your lab, that will be the volume of that reactor, right? What about aquifers? Where is the reaction taking place? In the pore space. So the reaction is taking place in the water. So this has to be water or the pore space. If the pore is fully saturated, the pore space is the same as the volume of water. But that distinction has to be made because this is milligrams of X per liter water. If you end up multiplying it with liter aquifer, which is your control volume, you will have dimensional inconsistency. Okay. So the only trick going from what you learned in your environmental classes to subsurface reactions is you have to account for the fact that not all of your reactor is where the reaction is taking place. The reaction is only taking place in that pore space. Okay. Otherwise, It's a pretty straightforward transition. Okay? So what type of reactions can happen? How do we model these reactions, right? So we need to somehow write this dc dt in terms of something else. Okay? So we have a variety of models. If I have a first order reaction, that's my first order reaction. P squared, and then I have these are three most common reactions that we try to fit, not because most of these reactions are truly first order, truly second order, or truly zero order, but having nice round numbers there makes our mathematics a little bit easier. So if I put instead 0.97 instead of a first order, I have a highly nonlinear equation, and if instead I say, well, you know, there's measurement errors, I'm going to make it 1, okay, no big deal, and then now I have a nice little linear equation that I can solve. Like, you know, so a lot of these first order, second order, or zero order are not because the reactions truly are first order. The only reactions that are truly first order are radioactive reactions. Radioactive decay is the only reaction that's truly first order. Rest is all what we call pseudo order reactions. Okay, because it's not just C, it's C plus something going to form something else, right? So this term is not taken into account; it's just pulled into that K naught, like, you know. So that's why it becomes a pseudo order reaction of some sort. Radioactive substances, on the other hand, decay by themselves because they have that energy to, like, you know, move from one. They have a built-in energy that will take them from one form to another. Most of the chemicals don't have that capability. So the only true first order reactions are radioactive reactions. Everything else is a pseudo first order or pseudo second order reaction. So where do we use, which type of reaction it works where? When do we use first order reactions? Or when do you think we should use first order reactions? Okay, so one way to do it is to do a batch experiment, and because dc dt equals minus kc, we can solve that equation fairly easily. And we actually, if I solve kc and c is equal to c naught at t equals 0, then the equation basically is minus kt, or natural log of c is natural log of c naught minus kt. So if I plot natural log of c versus t, I have some data, I fit an equation, and it turns out to be a nice little straight line, okay, and we say, okay, it's first order, okay. That's how experimentally we would come to first order, but not knowing anything, when would you say it's a first order reaction? Would you expect first order reactions at higher concentrations or at lower concentrations? How many are saying higher? How many have no? Okay, we have one. Okay. Lower concentrations. Okay, so how many are saying lower? 1, 2, maybe. Okay, lower concentration wins. Okay, so when the concentration is lower, reactions tend to be first order. Now, what's lower? That depends from species to species. There's no fixed number that says, but in general, if you're lower, you have first order reactions. Okay, so when we are at higher concentrations, what kind of reaction rates do we get? Zero order reactions. Okay, and if you have, when do we get second order? Second order reactions are when you need 2 moles of substance to react with each other, or when there is collisions happening. It can happen over an entire range. There's really no range where second order reactions cannot happen. Second order reaction, you have to really look at the mechanisms, or a mixed order, or even if you're looking at fractional order reactions that can happen. Again, the same idea is you try to fit this model, you raise it to power something, and you try to figure out what that n is. Okay? If the n is 0, it's a 0 order reaction. If n is 1, it becomes first order. If n is 2, it becomes second order. But if you randomly get n of 0.8, that's still a valid reaction rate. Okay? If you get a negative value, it typically means that there is some autocatalytic process going on in that reaction. Okay? So what's so good about Monod kinetics? Okay? Why do we look at Monod kinetics? Well, we use this a lot, right? Wastewater treatment. So obviously we use it in groundwater as well. So what's good about Monod kinetics? What do we know about this reaction type or this reaction model? Firstly, you need to know that this is a model. Okay, this is another way to represent dCdt. Typically, we use Monod models when there is a substrate limitation or there is some other limitation. You could also have an oxygen limitation, for example. Okay. So each of those terms, whenever there is a limitation, you put a multiplication of it and add a term that looks like this. This is called half saturation constant, and this is called maximum yield rate or maximum rate or maximum reaction rate. Okay. Only downside is if I want to use this for concentrations, if I want to track substrates, okay, there is C here, but this C goes away with this C, so that's dimensionless. Mu max has dimensions of 1 per time, just like a first order reaction. Okay. So I have C here, which is milligrams per liter, and then I have biomass rate, which is in some counts per liter or something. So to make the dimensions correct, I put a yield rate, okay, or yield coefficient, and the yield coefficient basically puts the concentration over x, okay, and it tries to establish a thermodynamic or a stoichiometric relationship between the two chemicals, the substrate and the biomass, which means you have to have some, what your substrate looks like, and you need to have a formula, chemical formula for a biomass, and then you can do a reaction and get that stoichiometric yield rate. Since we usually don't know because these are macromolecules, we tend to obtain that y experimentally as well. Some people put it in the denominator, some people put it as y, but generally the same idea. Mathematically, you have to remember that this is being done to make this equation consistent on both sides. Okay. If you are modeling biomass, then you don't need that. The other thing that happens in wastewater, which is why civil engineers get a bad rap, or this is why chemical engineers look down on civil engineers sometimes, is because we make approximations and we don't tell them. Okay, we generally assume that the biomass concentration is 1 and get rid of that x. Okay, it's not Monod kinetics at that point. Mr. Monod never said to do that. Okay, some civil engineer decided I can't solve this equation, but if I get rid of x, hey, I can solve this equation. So, but really we shouldn't do that. Okay, technically that biomass rate changes over time, but since we are looking at steady state and wastewater treatment in our activated sludge design, we just put a constant and get rid of it. We say we'll put 1, get rid of it, and everything else, the rest of the numbers will change to account for that. Okay, but that assumption is never written in any book, and a lot of people don't even know. If you ask them how to write Monod kinetics, they'll not even put the x. But that's not Monod. You need to have the biomass or something, because the reaction goes from something to something, and that needs to be captured. Okay. But Monod is not the only kinetics. There are Haldane kinetics. There are other types of kinetic models that we use, depending on what the kinetics is. But what's the advantage of Monod? The advantage of Monod is if you have very high concentrations, right? what happens? Why does it become zero order? Because Ks is much smaller compared to C, so the C and C gets cancelled and you will end up with 0 order. When the concentration is very low, this Cs is fairly small, but it's an addition to Ks, so we can remove it. But this has to be retained because it's a multiplication, so we end up getting a first order. So Monod kinetics automatically shifts from a zero order type reaction to a first order type reaction, depending on that how that concentration changes. Which is why it's a very flexible model to model reactions. The downside of it is there is concentration here, there is concentration here if we want to solve for concentration, so it's a highly nonlinear equation. And this is one of those equations that are called stiff equation. Okay. So I was talking about, when I was talking about differential equations, is you see these big transients for certain concentration ranges. Suddenly the model starts to go crazy. Okay. So if we make our time steps too big, you will get some bizarre numbers, like, so you'll have to solve them at very, very, very small time steps when those transients happen. Like, so new algorithms or adaptive algorithms like adaptive Runge-Kutta methods adapt your step size when they encounter the stiffness. They'll say, okay, this is stiff. They solve the model once, they check for stiffness, and if there's a stiffness, they'll say, I'm going to resolve that model with much finer time steps here. And oh, it's not stiff here, so I'm going to make that time step a little larger. Like, so that's how they kind of save on time, but at the same time get you the accuracy. Okay. So if you put this into there are stiff solvers for nonlinear, for solving, if this is part of a partial differential equation, like it would be in a groundwater transport model, you would use very similar techniques to solve it. Okay. But can we solve this analytically? No. So you'll have to solve this numerically, like, and that's what needs to happen. So that's kind of how we model. So the most common models are first order models, because most of the times in groundwater the concentration is fairly small. If the concentration is very high, like when you're near a source, you tend to model it as a zero order model. Okay. And Monod is used when you have a substrate limitation, like you have a microbial reaction that you're trying to model, but you are running out of your chemical. Okay. So there have been studies where people have gone and tried to look at what type of reactions or what is the driver for mechanisms for these reactions at different locations. Okay. So one of the things we see is, let's say we have a contaminated site, this reaction tends to be very anaerobic because there is a lot of substrate, oxygen goes away very quickly, like, so either due to biotic or abiotic reaction, there could be mineralization. At the edge of the plume, you will see aerobes operational because there is a lot of fresh water there, so they have oxygen. And then it goes to nitrate, manganese, iron, sulfate, and finally methanogens. Like, so if we go and sample across that plume, we will actually see the microbial communities change from aerobes all the way to methanogens. Okay. So which also means that if we want to model this plume, we have to put a variety of different reaction rates throughout our system and dynamically update it as we go through, because that areas will shrink, that plume will shrink or go up over time, right? So becomes highly complicated. Like, so what we do is generally we assume a constant reaction rate throughout our model. So that's probably one of the grossest assumptions that are made in groundwater modeling, is that we know our reactions are not proceeding at the same rate throughout our system, yet we assume one type of reaction rate and stick with it. Okay. We've made a lot of progress in putting heterogeneity of geology, but we have not made much progress in putting the heterogeneity of microbial, because those are very, very difficult to assess at a site. Okay. Because if I'm in an anaerobic condition and I put a well, I've just added oxygen and defeated the very purpose of what I want to sample. Okay. So sampling anaerobic conditions at the field, especially in groundwater environments, is a particular challenge because we have to put an invasive well, and in doing so we are introducing oxygen to our system. So we put a well, we let the reaction take place. Hopefully, if I have a lot of source, the system will turn back anaerobic, so I have to wait a long time and then take samples and do studies to find out what the rates are. That is just way too expensive, so we don't usually do it. Okay. So reaction rates, I talked about it. So what are elementary reactions? Elementary versus non-elementary reactions. Reactions you had when you first started school is elementary reactions. Okay, so elementary reactions are reactions that take place in single step. Okay. If they are taking place in multiple steps, then it's a non-elementary reaction. So any non-elementary reaction is made up of sequence of elementary reactions, which means if I'm able to write that reaction, for each of the elementary reaction, I can model it as with some rate constant, like using a kinetic model, and then I just add up those to form my entire reaction. Okay. The loading terms, as I said, for first order, you just take the reaction rate multiplied times volume, take the reaction rate multiplied the concentration times the volume, and in second order, it's either A square or AB, depending on how the reaction is taking place, times V. Okay. One thing you need to remember is dc dt, this k0, k1, k2 all have different units, and pay particular attention to that units, especially if you are taking data from the literature, because some people do it in moles, some people do it in milligrams per liter, and you have to convert accordingly, otherwise you will either overestimate or underestimate that reaction. I talked about monod kinetics. Generally in a closed growth cycle, what I have is a lag, so there is substrate, not enough microbes, right? Then what happens? I get into a acceleration phase, so very few microbes, lot of substrate, so great time to be living in that reactor, right? Then there is accelerated growth because because there was substrate, there was some multiplication of the microbes, and then the microbes just started multiplying, so the population just keeps exploding, and then you have somewhere where you hit the maximum population, and then these things start to slow off because there's a lot of competition for that food, so it kind of flattens out and eventually it falls off. Okay. So the most common microbe in subsurface environments are what type of microbes? Bacteria. Okay. What are bacteria? How many cells does a bacteria have? Mostly a single cell substance. Okay. Is it a plant or an animal? Figure it out. Anyway, so we have bacteria, and a lot of times at contaminated sites, the bacteria goes through this process, and especially when we hit this sixth process where there is death of bacteria, what happens is the bacterial population goes down. So as the contaminants reduce, okay, as the concentration of the contaminant goes down, there is less and less substrate. And initially there was a lot of substrate, right? So when we reduce it to the less and less of substrate, we have a lot of bacteria and very little substrate, so we start killing our bacteria. Okay. In wastewater treatment plants, what do? We take the solids and recycle it back for the very same reason that we don't want to kill off all the bacteria, so whereas here it's a one shot, we want to clean up this site, we don't want to add more substrate just because we want the bacteria to be going, so we wipe out that bacteria. So then what we see is we see elevated levels of protozoa, because protozoans actually graze on dead bacteria, so when you start seeing protozoa populations increase, it's an indicator of the fact that our microbes are dying. Okay, so now we need to figure out why the microbes are dying. They could be dying because, one, our concentrations are very low, which is a good thing, so when you start seeing elevated levels of protozoa, you can say that, hey, I'm actually cleaned up the site. Or it could also mean that the concentration is so high and it's so toxic that it's wiping out bacteria, and it's killing bacteria. It's too toxic for bacteria to stay in that environment. But protozoa is a very good indicator organism at contaminated sites, because they give us a good indication of what the microbes are doing, what the bacteria is doing. Okay. You could also have fungi, okay, and you could have other types of microbes, but generally you will only mostly see single celled. When you start getting into multi-celled, they start becoming bigger, and then the portal gets clogged, so sometimes we overstimulate this aquifer. We want to clean up this aquifer, so we go and inject microbes, or we inject nutrients to make this, to enhance the growth of microbes, and at that time what happens is the microbes just explode and clog up the pores, and there is no more water that's being transported, so it eventually ends up killing all the microbes, because there's no food coming to the microbes, and it goes away. The way we model microbial processes in wastewater treatment, what are the two types? So if you have a trickling filter, what kind of? One is attached growth and the other one is suspended growth, right? What do you think happens in groundwater systems? Is it more like a trickling filter, or is it more like a activated sludge which has more attached growth? Right, so we have more attached growth systems, because the solid matrix gives us a good place for it to attach. Microbes, if they are floating, they will encounter a pore that's small enough that they'll get attached to that to the process, and that's called filtering. That's one way to filter it out, right? So if they are suspended, we'll never filter them. So the same concepts that we use are used. I've showed you what this half-life is. Half-life is very commonly reported. When you do take half-life data from the literature, be very careful what half-lives you're picking. Generally speaking, if you do a reaction, if you do an experiment, a microbial experiment or a degradation experiment or reaction experiment in a batch reactor, that rate will be much higher than what you will encounter in groundwater, because you have much smaller pore space, much less mixing. Okay. So if you do an experiment in a CFSTR or a batch reactor, your conditions are a lot more ideal than what it is in the subsurface. So if I were to do these experiments in the subsurface, the reaction rates will be much lower than what you will have. In other words, if you take batch reactor data and put it into your model, you will overestimate degradation. If you overestimate degradation, you will underestimate concentrations, which is a bad thing. Okay. So the key is to simulate your experiment as close as possible to what's happening in the field. Okay. Column studies are slightly better, but they're not good either, because the velocities at which we do column studies are much higher than average groundwater velocities. Okay, we just don't put 0.1 or 0.2 feet per day going through our column. Our column will have like few liters per day, or tens of meters per day. of velocities going through our column. So that tends to be a lot faster. When that happens, there is not enough time for reaction to take place. So you will end up underestimating the reaction rates than overestimating the reaction rates, okay? Which at least is better than overestimation, because now you are saying the reaction is not happening at the rate at which it's happening. So you are certainly putting out mass transfer limitations or limitations associated with the fact that you're not letting enough time for the reactants to stay in the reactor for the reaction to go to completion or to go to whatever rate it went. So getting data for putting kinetics or putting models, putting like react is extremely difficult. So a very common approach is to use first order, and because there are reported half-lives, and we can use that reported half-lives. But reported half-lives can be reported in atmosphere, they are reported in like water, they are reported in wastewater. So be very careful when you pick that number, because it has to represent or as closely represent what's happening in your groundwater system, not what's happening in a wastewater treatment plant or in an atmosphere or in a lake, which will have very different half-lives. So how do we estimate these parameters? Again, as I said, like by and large, the way we do it is estimate it in the lab, okay, and then we put it in the field. Okay? There are places where we can calibrate the model and back out, okay, but usually the reaction rate is not the only thing that we don't know. We don't know dispersion, we don't know advection completely. So we are calibrating a model to back out reaction, but we are also calibrating it for dispersion, we are also calibrating it for advection rates. Like, so there are multiple parameters that you're calibrating, and calibration is a non-unique process, which means a set of combination of values of your calibrated parameters will give you one result, another set will give you exactly the same result. And when that happens, so you don't know whether you got the right reaction rate or not. Okay? So some people report it as pseudo reaction rates, like or they report it as calibrated reaction rates, just to kind of make it separate from the actual reaction rates. But it's not an easy exercise, especially if you have nonlinear models that include monode kinetics or higher order kinetics. It's difficult. So a closely related concept is mass transfer. Okay? So most reactions, we model them as kinetics, okay, because our substrate eventually goes away. Like, and also conditions are such that the rate of reactions are not the same. Like the thermodynamics in the subsurface are such that the rate of forward reaction is not the same as reverse reaction. Now, what happens in subsurface is, at the very least, we have two phases. Like one is the water phase, and the other one is the solid phase. Okay, so most chemicals can coexist in either of these two phases. So they can stay in liquid phase, or they can stay in solid phase. So instead of traveling just along the water path as it would in a single phase system, and of course it would undergo some diffusion along the process, what will happen is I can have it go into the solid phase, transport through the solid phase, come out, go back, come out, so it takes a much more tortuous path, or like much more slow path. So if I were to put a solute in a pipe with the water flowing at the same velocity as a subsurface system or an aquifer flowing at the same velocity, the solute will come out faster in the pipe than it would in the subsurface system, because unless it's chloride, which is fairly conservative, but most solutes would come out much slower in the subsurface system, right? Because they undergo this process called retardation. The retardation is simply that they can go into the solid phase and come back, and so they are not traveling just in the liquid phase. They can go into the solid phase and come back. So what is the process where something goes from a liquid phase to a solid phase? Sorption, adsorption, desorption. Sorption is a generic term for both adsorption and desorption. Adsorption is what? So it goes from liquid phase towards solid phase, or there is a net movement from the liquid phase to solid phase. It does not mean that there is no movement from solid phase to liquid phase, it is just much smaller compared to. So the direction from liquid to solid is much faster than from solid to liquid. So there is a net movement towards from liquid to solid phase. What about desorption? So the movement from the rate of reaction, like you can think of this as a reaction. The chemical is just moving from one phase to another phase, just like we form ice, water to ice, ice to water, right? Where is the kinetics faster? Ice to water is a much faster kinetics compared to water to ice. I mean, you have to overcome a huge energy gradient before you can make that phase change, whereas on the other hand, the phase change is much easier, right? So the same thing, like sometimes adsorption is much faster, sometimes desorption is much faster. You would hope and pray that adsorption is much faster than desorption, because that takes away your contaminant or slows it down considerably. If you are designing a filter, or if you are designing anything based on adsorption technology, the whole idea is that kinetics is, it's kinetically controlled, and it goes to that place much faster than it comes out. Okay.
So is sorption the combination of absorption and adsorption, or adsorption and desorption?
Okay, that's good. You brought in a new word. What is absorption? Right. So adsorption is when it's strictly on the surface of the soil. Absorption is it can go inside the soil. Okay. Desorption is when it comes out. When it comes out, we don't care whether it's coming out from the surface or whether it's coming from inside, right? So since we don't care on one side, we shouldn't care on the other side too. So adsorption, absorption, desorption are all lumped into sorption. Okay, we don't have deabsorption, desorption. Okay, so deadsorption, like so if it comes out, it's desorption. Okay, if it goes in, it can be ad or ab. Okay, so an absorption is very similar to liquid mass transfer. There are infinite number of sites where this chemical can essentially go into the solid phase. On the other hand, adsorption means there are limited number of sites on which this chemical can stay, and once those sites are taken, your reaction slows down quite a bit. Okay. Even under equilibrium conditions, what would happen? The rate at which the molecule goes into this chemical is the same as the rate at which it comes out. So the rate, adsorption and desorption are happening at the same rates. The rates of those are the same. Okay. If we have absorption, so yeah, before that, so the chemical is moving, right, and mass transfer is happening. Okay, and mass transfer can also be kinetically limited. Okay, because your velocity, your groundwater is moving. Your solute is sitting here, and it wants to go to the solid phase. Okay? It has to go from here to here, right? So the water is moving very quickly. Okay? There is very little chance for this molecule to go in there, right? So it has to diffuse out, and at least it has to go to that surface, and then from that surface jump onto the other side. Like so, when that's happening, if this is moving very fast, it may not have enough time for that solute to go from the bulk solution to the surface and then cross over to that other side of the interface. So it creates what are called mass transfer limitations. Okay. So if you're running columns where you want to do mass transfer and get rid of something, you want to run it at some fairly slow speed. Like if you run it too fast, you won't have enough mass transfer. So chemies worry a lot about keeping the reactors slow for the reaction to take place, but at the same time, if the reaction runs slow, they're making less of a product, so which means less of a profit. So it's a downer for them. So they want to be as fast as possible, but at the same time they want to do mass transfer. Okay. In groundwater systems, our velocities are very slow. A lot of times the rate of our velocity is much slower than the time it takes for the mass transfer to achieve to get to as close to equilibrium as possible. Okay. So, because we are having a slow moving water system, we tend to achieve equilibrium in mass transfer. Okay. So, that is what is called as the local equilibrium assumption, or LEA. Okay. So, LEA basically says that okay, is what it's saying is that since the groundwater velocity is very slow, I have no rate limitations for my mass transfer. The reaction will go to completion, and the rate at which adsorption takes place, or or absorption takes place, is the same as the rate at which desorption takes place. Okay.
How do we distinguish between rate limitation and retardation?
Yeah, right. So we'll get to that. Okay. So if we have rate limitation, right, the chemical will move faster. If you have retardation, the chemical will move slower. So I have a column, two columns, right? Here the water is moving very fast. Okay. There is not enough time for this chemical to go here. Okay, which means it will tend to stay in the water. So my concentration will come out at the end of the column. If I plot C versus T, initially I am just getting clean water, and over time it will go up, and if I have a constant concentration, this is what it will do, right? What happens if there is adsorption? It will shift, and instead of the center of mass coming here, it is now shifted by certain time, right? So that's what adsorption does. It tends to retard, because the path is much more tortuous than a straight path. If I have mass transfer limitation, it means that this water is moving very fast, so there is not enough time for it to go and adsorb. So my breakthrough curve will look more like this, more like a conservative solute than it would for a retarded solute.
You are saying the second phase, if you want to remove the contaminant, the will again shift like that?
If you are interested in a desorption mechanism, where you say, okay, I have some chemical in the solid phase and then I want to remove it, if I were to move it very slowly, my contaminant profile will look like this, right? But if I'm moving very fast, this will shift much onto the other side. So in the desorption, retardation is when I'm generally looking from water to the liquid and then back. If you're strictly doing desorption, then you have to use kinetics to describe it, because that is the dominant process. If it's equilibrium, you're not removing anything, like you're just the ratio still stays the same. So we use local equilibrium assumption, or we say because of local equilibrium we'll end up with thermodynamics. So what does it do to our models, right? So what it does is, so I need to write my reaction. I'm going to write my mass balance, which says accumulation is in minus out, plus or minus reactions, right? So this is my generic mass balance. Okay. So this in minus out could be due to advection, could be due to dispersion, right? Here these reactions could be biotic, abiotic, or physical. Physical being mass transfer. Okay. So these two will remove the contaminant. This will just change it from one phase to another. So they can all be kinetically controlled. Like, so I can put a similar first order type model, okay? But the downside is we have some site limitations, right? There is a maximum amount that my solid phase can take before, and then it'll stop taking things. So the way I write my reaction usually is R of Cs minus C, or K of Cs minus C. What this is saying is, it says that there is an upper limit or some saturation limit. Once I hit that, I'm under equilibrium conditions. The net reaction stops. Okay? So same thing we do when we do Streeter-Phelps model and do oxygen sag, because our oxygen is, there's very little oxygen that can be in our water. So once the saturation hits, we say there is no more oxygen coming into our system. Okay? So the same concept is used for adsorption. Okay? The same concept is used when we have another liquid, say a non-aqueous phase liquid, say gasoline or something that doesn't really dissolve in water, or can stay as a separate phase. There could still be liquid-liquid mass transfer. That liquid-liquid mass transfer is also modeled in a similar way, with this C as being the solubility of that chemical. That's the maximum you can take in the water. Okay? In this case, this would represent some adsorption, maximum adsorption capacity. So we'll be writing it in terms of solid phase instead of liquid phase. Okay. When we have equilibrium, right, we would have to write two mass balance equations again, one for transport in liquid phase, okay, and here we would have accumulation in water, okay, equals the pollutant moving in and out in water because of advection plus dispersion. Okay. I'm going to neglect all of the reactions and just look at mass transfer. Okay. So there is some reaction, my mass transfer reaction, kinetic reaction, okay, that actually moves what? That actually removes my contaminant, right, because it's in the liquid phase, now it's gone to the solid phase. So there is something being removed, and then there is something being added, which is the chemical is moving from the solid phase and being added to the liquid phase. Okay. So the chemical is moving from liquid phase to solid phase to liquid phase, right. So I'm going to write some reaction, and I would put a minus sign. This is liquid to solid phase, so it's being removed, plus some reaction going from solid to liquid, that's being added to our system. Okay. Similarly, if I track this in the solid phase, okay, usually in the solid phase there is no transport, so this term goes away, right. Now what went from liquid to solid phase is added as a plus, and what went from solid to liquid phase becomes minus. Okay. So if I solve this differential equation, I will end up getting concentration in the water phase. If I solve this differential equation, I get concentration in the liquid phase. Okay. Now, if the rate under equilibrium conditions, what happens? Okay. This and this will be one and the same. This and this will be one and the same, right? So if I sum up these two reactions, because I don't have any other reaction I have removed. It just boils down to what's transported out. Okay. This will be written in terms of del T. This will be written in terms of density, because the solid phase concentrations are written in milligrams per kilogram. So, I just have to convert it using bulk density. So, I have two unknowns, C and S, one equation. So, I need one other equation to solve this, because I have two equations, I need two equations for two unknowns. If it was kinetically controlled, this kinetics and this kinetics will not be the same, and I would have one equation for the kinetics and one equation for mass balance, because there is a net movement in one direction. Okay. So, but in equilibrium, these all vanish, these all get removed, because they are one and the same, and I get this. But I need another relationship that says what is the solid phase to liquid phase relationship. Okay. This is called what? An isotherm. Okay. So, the most common isotherm is linear isotherm. Okay. Linear isotherm represents absorption process, because the concentration just keeps going straight. Okay. Which means as my concentration increases, I have no limitations on the solid side. I can still absorb, just like I can keep on adding water to milk, and it will just absorb it, right. So, same concept. Okay. Sometimes we have site limitations. So, we get S versus C, which looks like this, okay, which means that at higher concentrations there is much lower absorption than at lower concentrations. It's almost like you drive into a parking lot. If your parking lot is empty, you have a lot of sites to choose from. You will pick the closest site and sit there, or park your car there, or park your bike there. On the other hand, once the parking lot is full, you have lesser and lesser chances of getting a parking spot, and when it becomes completely full, you have nothing to do but get out of that parking lot and go somewhere else. So, that is what the site limitations do. Okay. If you have site limitations, concentrations in the water phase will be much higher than concentrations in the solid phase. So, modeling that is important, because that would mean that your system is not removing or retarding that chemical as it would. Okay. So, this can be modeled using a variety of different types of models. Most common models are Langmuir model, Freundlich model, there are whole others. Yeah, there's a whole bunch. So, Brummer, Emmett, Teller, or whatever, BET model, there is Temkin model, so. But the most commonly used ones in groundwater are linear, Langmuir, and Freundlich. They all come from different. The Freundlich and Langmuir do the adsorption process. Linear does the absorption process. And why is this caused? Where these models differ are why are there site limitations? Langmuir model assumes that there is only a monolayer of sites, and that's where it happens. But what Langmuir model also assumes is that each site is a homogeneous site. Any site is equally likely to be occupied. Freundlich model, on the other hand, assumes that there are heterogeneity in sites. So, it keeps on exponentially, keeps going up. It never truly flattens out. So, then you can have things like, if you have multi-component mixtures, you could have competitive sorption, because your benzene and toluene, now they are competing for the same site. If benzene gets there first, benzene takes it. If toluene gets there first, toluene takes it. Usually, the lower the molecular weight, the faster the molecule moves, which means it has a fast car. It will get there. If you have an old car, you are slower, so you don't tend to sorb. So that's competitive sorption. The opposite can also happen. It's called cooperative sorption. And what the cooperative sorption does is, you have a substrate, it goes and sticks, okay, and that itself becomes a new site for the substrate for a second chemical to come and sorb onto it, like, so that's called a cooperative sorption model. Like, so competitive sorption means they're competing for same sites. Cooperative sorption means one component creates new sites for the other component and enhances its mass transfer. Okay, you can have similar competition in reactions as well. Okay, so you could have two chemicals, and microbes preferentially will degrade one chemical as opposed to another chemical. Then that's a problem. But you can also use the opposite, what's called as a co-metabolism, where you put a little bit of one chemical and trick the microbes and then put another chemical. So trichloroethylene, which is a dense non-aqueous phase liquid, a lot of times was treated using co-metabolism process, co-metabolic process, where we put toluene and train the microbes to chew up toluene, which is a much easier compound to chew, and then slowly we take off toluene and put TCE, and the microbes will just chew it because they think, oh, it's toluene, like, so I'm gonna remove it, like, so if you just give them TCE initially, they will not use TCE because it's a xenobiotic. They've never seen it. They don't know what it is. It's very hard to break those chlorine bonds because they just don't have the energy. On the other hand, it's a lot easier to break that aromatic methane methyl group bond in toluene. So once they learn how to break that, they'll go and break that chlorine bonds and then start using up that as well. So that's called a co-metabolic process, or like, co-metabolism. So used quite frequently in bioremediation studies, like, so of course the downside is you have to go and ask the pollution control board or what the equivalent of it and say, I'm going to inject another pollutant to clean up the pollutant is a difficult sell sometimes. Like, it's hard for people to understand that you can actually put a pollutant and remove another pollutant. So it's not widely popular, like, but or sometimes when you do it, you have to do it with a lot of monitoring that it becomes expensive, but nonetheless it's doable. So what else about mass transfer? So the mass transfer is, if you do equilibrium, what happens is you end up getting one equation, which is a differential equation, and then one equation which is an algebraic equation. If you do kinetic description, you will end up having two equations which are both differential equations or partial differential equations. Which one's easier to solve? One differential equation and one algebraic equation, or two differential equations? Two differential equations obviously is much difficult to solve. So equilibrium, the side effect of equilibrium is it makes your mathematics a little bit easier too. Of course, if you use linear isotherm, you will have a linear differential equation. Remember, we had a linear differential equation. If you have a linear isotherm, you'll maintain that linearity. If you have a nonlinear isotherm, you will turn the partial differential equation into a nonlinear equation, and again that equation becomes stiff. So even small changes to your Freundlich isotherm, or like, using Freundlich exponent, can change your breakthrough curves quite a bit. Okay. So any questions on mass transfer? So we're right at 4 o'clock. So the next 30 minutes are largely for any discussion. Okay, before that, if you want to do partitioning or look at how chemicals partition between different phases, we use some indicators. If you want to see how it partitions to air, vapor pressure is a very good indicator. Vapor pressure basically is what? Vapor pressure is pressure exerted by what? Molecules present in a closed container. What does it do? So I put molecules in a container. One thing we know of molecules all have ADHD, so they can't sit in one place, so they keep on hitting things. So they end up hitting the walls of the container at some time. and that is the pressure exerted by the molecules on that. Okay. So that is partial pressure. So if I have a mixture, here is a mixture of gases, right? 75% nitrogen and 21% oxygen, 10% carbon, whatever, like, we add all up. So they're all exerting pressure on the walls. Okay. So that is just called partial pressure. And Dalton came out and said what? You know who Dalton is? So what did Dalton say?
Pressure accepted by each component is equal to when it is present alone.
Did Dalton say that?
Total pressure is sum of all.
Correct. That's what Dalton said. Okay. So an offshoot of that is if a molecule is present in a mixture, it's going to act very similar to how it would act if it were to be present alone, right? But of course, because it's present in a mixture, it only has a smaller mole fraction. Instead of being mole fraction 1, it's got a mole fraction of some x less than 1. So he was saying that the way it interacts is the same, but the total pressure is the sum of equal to all the partial pressures that are associated with it. Like, so in other words, Dalton says if you have a mixture of gases, the interaction of the mixes of these gases is not as important as how they act by themselves. Like, and because of that, we can take the mole fraction and multiply times the pressure exerted by the gas. So what is the maximum pressure that's exerted by the gas? So instead of having a mixture, if I just had one gas, right? If I had only one molecule, one type of molecule in that gas, what would be the pressure exerted by that gas? That is the vapor pressure, basically. So vapor pressure is the pressure exerted by the gas that is in contact with when it's fully saturated. Okay. So if it's in contact with the liquid that's causing the vapor, so you've saturated that head space or the air space with that molecules, and the pressure that gas exists is that vapor pressure. Okay. So the vapor pressure is the maximum pressure that gas can exist, but if it's part of a mixture, it will get reduced proportionally based on mole fraction. Okay. That's because of Dalton's law of partial pressure. Okay. So what is solubility? So it's a maximum concentration in a solution. So very similar to Dalton's law of partial pressure, what we say is there is an upper limit to how many molecules can be put in a liquid phase. Okay. Of course, the molecules are just not as active in a liquid because there's a whole bunch of solid molecules pushing them down instead of freely moving, but still they do exert some pressure, and solubility is the measure of that pressure, like in a concentration. What about octanol water partitioning coefficient? KOW. Correct. So it's the ratio of the concentration of some chemical in octanol versus. So it's looking at solubility in octanol to the solubility in water phase. Okay. What is that? So why do we pick octanol? What's octanol? C8H C8H. What's octane? C8H18 is octane. Pull out a hydrogen, put in a hydroxyl, you will get octanol. So C8H17OH is your octanol, right? It's an alcohol. So of course, depending on where that OH group is, you can have different types of octanol: 1 octanol, 2 octanol, 3 octanol, 4 octanol, possible. 5 octanol is not possible because that will be same as 3 octanol, just from the other direction. So but typically we use 1 octanol as a reference when we do octanol water partitioning coefficient. So octanol is very, so what happens is we usually put octanol, put water, introduce a chemical and see how it partitions. So that ratio basically tells us how this chemical would partition into organic substances. Okay. A lot of organic substances, organic pollutants, prefer soil organic matter. So they preferentially sorb onto soil organic matter. They could conceivably sorb onto mineral matrix because of steric properties, like because the size could be such that they'll go and happily sit there. That's a steric reasons why the sorption occurs, and also because there could be some chemistry that's going on at the surface that will cause that sorption to occur. But in general, octanol, concentration will partition to octanol. Octanol is also a good indicator for fatty tissues in our bodies. So fish, okay, you have contaminated groundwater, you pump it out, put it in a fish farm, grow fish, eat that fish, what happened? So there's biomagnification. Why is there a biomagnification? Because that 5 milligrams of benzene that was sitting in 1 liter or 2 liters of water, 1 liter of water has now gone into 5 milligrams of benzene in that 15 grams of fat that's present in that fish, or 10 grams of fat present in the fish. So the concentration has just gone up because my denominator has become very much smaller, so again, to measure biomagnification or those kinds of effects, octanol is a very good indicator, because it's a representative organic compound used to represent organic matters. So in groundwater systems, most organic pollutants will sorb onto organic matter in the soil. Okay, so that's called soil organic matter. Now, what's the soil organic matter? How did soil organic matter get there? How did organic matter get into the soil? Decay of material. So there are plant roots and whatnot, they decayed. A lot of times there are fossils because there is deposition. So there was some plant or animal sitting there, and then there was deposition that took place that killed this plant, and it decayed underground. So you form soil organic matter. So that process is called diagenesis. That's where if that process goes to completion, we'll get fossil fuels. But on the upper portions, you don't get that much diagenesis because there's not much organic matter. So you don't make crude oil, so it's a much slower process. But so there is soil organic matter. Typically, that soil organic matter goes down as you go down into the aquifer because you get clear sands. There's very little soil organic matter. But even if you have less than 1% of soil organic matter, all that organic contaminant will go into that soil organic matter. Now, soil organic matter is a macromolecule. It can contain many different types of functional groups. It can vary depending on what kind of plants you have or what actually formed that soil organic matter. So soil organic matter by itself is not a very good indicator because that soil organic matter varies from place to place to place. So instead, what we do is we use another measure called soil organic carbon, because then we say, okay, we know this is organic carbon. So we measure soil organic carbon and then normalize it to soil organic carbon. The partitioning is often represented as milligrams of solute per kilogram of soil organic carbon. So that's because soil organic matter is not a homogeneous substance. It can vary from across the world. So if I say soil organic matter in the US, it can be very different from what the soil organic matter in India is. Even within India, it can vary. So soil organic carbon gives us a more normalized measure. Okay. How do we measure soil organic matter? Has anybody measured it? That's a very crude way of doing it. The other way to do it is to oxidize the soil organic matter using dichromate or some sort of a strong oxidant. You burn it and then you say how much you burned. Soil organic carbon, on the other hand, you want to find that functional group of carbon So you have to do, you have to use a CHN analyzer, which is a carbon, hydrogen, nitrogen analyzer, and then calculate what that carbon is. The other option is to do a total carbon, and then subtract out a DIC, which is a dissolved inorganic carbon, and then you will be left with dissolved organic carbon. So there are a couple of ways of doing that. Okay. So for a lot of chemicals, you can look at solubility, the log K or W, and the vapor pressure to figure out where that chemical is likely to be. If this number is large, it tends to be in water. If this number is large, it tends to be in organic matter. If this number is large, it tends to prefer atmospheric phase. So the chemicals partition into different phases. Okay. So there are two types of partitioning that can happen. We talked about the soil-water partitioning. In soils, we can have air-water partitioning, and the concentration of air to the concentration of water is constant if equilibrium conditions persist. Okay, and that's called Henry's law constant. Okay. There is another law called, before we go to Henry's law, let's talk a little bit about it. So we put concentration of water, typically in milligrams per liter. How do we measure concentration of air? What are some of the common units for measuring concentrations of air? Well, because it's the pressure exerted, right? So we sometimes use pressure to measure our concentrations in air. We can also say milligrams per liter of air. That's also possible. The only downside is the liter of air depends on what the pressure and temperature are. The liter can change quite a bit depending on what pressure you're putting on it. So we tend not to rather use pressures. So to convert from pressures, we divide it by RT, R being the gas constant. This is just coming from ideal gas law. We can back out. Okay. So always keep track of what units that Henry's law constant is. But what Henry's law constant is telling us is, it is saying if I have water and air and I have some molecules, okay, all in water at time t equals 0, then after some time they will move and partition into two phases if they can. And what it says is that the ratio of the concentration in water to concentration in air stays the same. Okay. In other words, every time a molecule comes here, another molecule goes there, and then that ratio stays constant. Okay. So that's based on the concept of equilibrium. But Henry's law constant means it's the chemical in the water. Okay. So it is only applicable to dilute solutions. Okay. So if I have let's say a mixture of okay, so that's phenol and that's benzene. Okay. So if I have a mixture of phenol and benzene with mole fractions equal to 0.7 and 0.3, then this is not a dilute solution. This is a concentrated solution. I mean, this is a large amount of phenol and a fairly large amount of benzene. Okay. So you will still get equilibrium at some point. Some molecules will escape. They both are volatile, so they'll go into the air phase. If you want to calculate what that concentration is, we say that the total pressure is equal to the vapor pressure of benzene times the mole fraction of benzene plus vapor pressure of phenol times the mole fraction of phenol. Okay, that's coming from Dalton's law of partial pressure. Okay, and we also say that the vapor pressure, the ratio at which these molecules are is proportional to their mole fraction and their vapor pressures. That's Raoult's law. Okay. So, if you have concentrated solutions, we use Raoult's law. If you have dilute solutions, we use Henry's law. But this is to model the air-water mass transfer, okay, or liquid-air mass transfer. So, if you have multi-component mixtures, one other thing about Henry's law constant. In groundwater environmental literature, we always put the concentration of air first, concentration of water in the bottom. Chemical engineers usually reverse it, and that's called Ostwald's law as well. Sometimes they call it the Ostwald's law constant, and they write concentration of water to concentration in air, because they are trying to do scrubbing, or like they are trying to remove something from the air phase into the water phase. We are usually interested in removing something from the water phase into the air phase. So we put air first, they put water first. So when you have dimensionless Henry's law constants, be very, very careful to figure out the way it's written. Otherwise, you will have huge errors. Okay? You can also look at henryslaw.org. Only thing is they give you the ratio of water to the air phase. So they give what's called as the Ostwald's law, because this was compiled by chemical engineers, and they usually use that notation. Cool. Sorption, we talked about sorption. A lot of different things that can happen. A lot of interest has been, if we sorb these chemicals, how will they desorb? Okay, how quickly will they desorb? Okay. There was a lot of work done that shows that desorption actually proceeds in two phases. So there is a fast phase of desorption followed by a very slow phase of desorption. The reason for that is, if the chemical is in rubbery domain, and so the organic matter is made up of what is called glassy and rubbery domain. So when the diagenesis is done, it gives you a much nice crystalline structure. On the other hand, some of the organic matter is loosely, it's not in a good structured way. When an organic chemical goes into that loosely structured portion, it can come out, it's got a lot of sites, so it tends to stay there. But if it goes into that structured portion, getting out becomes difficult, because it has to overcome that structural barrier to come out. So the fast desorption happens out of the rubbery phase, slow desorption happens over the glassy phase. So people have kind of said that, we've seen this behavior where about 80% of the stuff desorbs initially, and then the remaining 20% takes forever to desorb. The downside is, a lot of our concentrations are so low, right? I mean, our drinking water standards are so low. So even though that 20% is left behind and it's slowly desorbing, it can cause years and years of contamination. And that's been a big issue in terms of retardation, in terms of sorption for us, is when chemicals sorb and then they're starting to desorb, that process can be very slow, and you may see a lot of good recovery initially, but later on it will just become it becomes what's called as a fat tailed, the tail just keeps on continuing, and slowly bleed out. So one good way is to plot this on a ternary diagram and see which chemicals have an affinity to air, which communities have affinity to water, which have affinity to soil. So I show you the calculations in those notes, you can kind of follow that. So, and I also give you some R code to do the ternary plot, and so you can look at that as well. So any questions? So we kind of covered all the processes. There are a couple other processes that are important, especially in recent years. We've been very interested in looking at microbial transport through groundwater systems. If you have a septic tank that's leaking, it'll probably put some coliforms, it'll put some microbes. How do those microbes travel? A lot of interest in using nanomaterials for remediation, which means that the nanomaterials are even smaller particles and how they travel. So there are a couple other processes that are used commonly. One process that in particular that's useful is how do they get filtered out? Okay, so we have colloids or colloidal sized particles, very small particles, and they're moving through the subsurface. So microbes like viruses, bacteria tend to be colloids. Okay, so what's a colloid? Yeah, particles typically less than 1 micron are colloids. Colloids also have a very interesting characteristic, that is colloids basically are suspensions. Okay, since they are so small, they will not go down. Okay, they will not settle. Okay, but if you have big particles, what will happen is those particles will start to filter out. Okay, so when the colloid hits a pore that's a much bigger pore, it tends to be on it, so it gets filtered out. Okay, colloids are also suspensions, right? So if you have organic matter in colloids, sometimes the chemical will stay in that colloidal phase, and then it will move out without getting sorption. So colloids can facilitate transport of other chemicals. Okay, so that's called colloid facilitated transport. And colloids can also have can get filtered out. Okay, so filtration theory. How many of you know what filtration theory is? Basically, how do we design filters? Nobody? Okay, so we'll talk about it tomorrow. Then, so basically, there is something called a filtration theory and filtration efficiency, and we strain out just like we take buttermilk and strain it out, right? Like to get when we do buttermilk, that's what we do, straining reaction. The colloid particles, basically, those are removing colloid particles. We're straining out colloid particles because your curds or milk is a colloid, basically, like it's a suspension. If you freeze it, what will happen is the water separates, the milk separates, like but in normal times the particles are so small that they will never separate. It'll take a long time unless microbes come and chew on them and make bigger particles, and then it settles out a little bit. But which is that's how the curd process is. That's how you make curd, and when you strain out, you're straining out the colloids, like you're making those particles bigger, and then you're removing it from the water phase, like you're separating that solid from that water phase, and that's what filtration theory does. Like, that's how filters work. You want to remove the particles by one, providing a steric hindrance, which is you make the pore so small that they can't move through it, and not only that, they sit there and they aggregate to form bigger particles and make it even difficult for even smaller particles to move through that system. Like, so that's called straining that happens on a filter. So colloids, nanoparticles are all modeled using these colloid filtration theories. So that's a very common way in which we model viruses, bacteria, or any other colloidal substances. Nanoparticles, it's a crude way to model nanoparticles. Of course, nanoparticles being so small, their diffusion process is also a little different. They go through what's called as a Knudsen diffusion as opposed to regular Fickian diffusion that we model. But first cut models generally are do the colloid filtration theory to look at this. So we'll look at some of these. We have a class?
Next class actually.
Oh, okay. I thought we had till 4:30.